Good morning, everyone. My name is Sam Choles from the Paper Manufacturers Association. Thank you for joining us for our second webinar in our Young Engineers webinar series. If you missed last week's, I will post the YouTube link in the chat a little bit later. In terms of housekeeping, please remember to post your questions in the Q&A section and use the chat section for any general comments. It's just a little bit easier to answer them. We have some really interesting projects today from some really bright young minds, and these projects aim to contribute to the circular economy, to society, and the sustainability of our sector. I'll hope you will join me in giving the students a welcoming and virtual round of applause. It's not an easy task to present to a virtual room. So yeah, sometimes the nerves do get in the way. I'm nervous. I had no power this morning, so I was a little bit edgy this morning when I woke up. There's been a slight adjustment in the order of our events today. Jane Maloney, Executive Director of PAMSA, will be doing the welcome as she's got some pressing commitments to get to, and Julie Borland, who leads our process unit, will do the closing remarks. Let me just introduce our speakers quickly. We've got Hester Oosthuizen, Norma Malenze, Nasreen Gadi, Peter Nambe, Lovejoy Dewa, and Musamba Banza. If you're not familiar with our sector, we have a short video and I hope you will enjoy it.
Wood. We use it every day. In our homes, it holds up the roof. It bolsters the sofa. We walk on it, eat at it, we play with it. In paper, it keeps our to-do lists and colors our birthdays, dispatches the news and holds words we love to read. It carries our coffee and cushions our belongings, protects our pizza, keeps juice and milk fresh. It wipes our tears and mops up our messes. It's an artist's blank canvas, a fresh, clean start. Paper, easy to recover and recycle, for reuse in 1,000 different ways. And the wood that makes paper? It's sustainably grown, renewable, specifically planted, harvested and replenished to preserve and conserve. Together, wood and paper provide careers and livelihoods for thousands: foresters and environmentalists, researchers, machine operators, engineers, and recycling collectors. Responsibly produced wood and paper products enrich our lives, make our jobs easier, and our world more sustainable. Wood, paper, renewable, recyclable, remarkable.
I watched that video 1,000 times and I still get goosebumps. So without taking up too much time, I'm going to hand over to Jane Maloney.
Morning, everybody. I hope you can hear me. I seem to be having some connection problems. We're really excited that you have joined us today. The pulp and paper sector partnered with the Department of Science and Innovation and on a sector innovation fund to promote research, development and innovation. And the Tshwane University of Technology, the Vaal University of Technology and the University of Pretoria and UNISA have all been involved in having students with us. And today they're going to be giving their presentations. We work in a fantastic sector, and as you all know, our sector has a very important part to play in fighting climate change. And that is why I'm pleased to tell you that I will be going off to COP26, and today I have a fiber circle logo behind me, which is all about the circularity of the sustainable wood product. So without further ado, I would like to welcome you all and wish you students good luck. I'm sure you will do a fantastic job.
Thank you, Jane. Thank you so much. Let's get the show on the road. We have first up we have Hester Oosthuizen, Her project is the preparation of cellulose films, extrudates, and fibers facilitated by mixtures of ionic liquids with choline chloride. These are big words for me, even in the communications field. So Hester, I'm going to share my screen with your presentation. And just as we rehearsed, you just need to tell me when to click, or I'll just listen for your audio cues. I just need to change something quickly and then we'll get going. Hester, the floor is yours.
Morning. Thank you, Sam. Morning, everyone. Yes, I'm Hester Oosthuizen. I'm a student at the University of Pretoria under the supervision of Walter Fokker in the Institute of Applied Materials. And I would like to tell you a bit more about my master's project, where we used a mixture of imam acetate and choline chloride to prepare cellulose films, fibers, and extrudates. So a few years ago, there was a 10-year challenge on social media. And today I would like to present to you the winner of the 10 million year challenge in my book, The Dinosaur. Unfortunately, this modern dinosaur is responsible for a lot of pollution, right from its production up until the point where little Tommy doesn't want to play with Mr. Dino anymore, and Mr. Dino spends the rest of his very long life on a landfill. We are all aware of the negative effect plastics have on the environment, but we are also keenly aware of the value that it adds to our lives. Not only does it prolong the life of produce, so we are limiting food waste with the plastic, it keeps us warm, it is a really handy material that is not going anywhere. So we should try to find a way to make it more sustainable. And cellulose is uniquely positioned to be an alternative raw material. You can go to the next slide, please. Yeah, so cellulose is uniquely positioned as an alternative raw material to prepare biopolymers. Not only is it abundant and renewable, as it's the largest constituent of plant biomass, so we can literally just plant more trees. We can also extract it from waste streams, agricultural waste like corn cobs or stems. We can extract cellulose from that, and these waste streams are not competitive food sources for people. So we are not taking the food out of someone's mouth to prepare a plastic bottle. Cellulose is also biodegradable, which should help with the end-of-life pollution of most of the products that we have in our lives. And it has other interesting properties like being biocompatible, which means we can use it in biomedical applications as wound dressings or stents. And it's also a very good polymer for fiber applications. So if cellulose is so wonderful, why haven't it taken the world by storm? Well, unfortunately, cellulose is largely insoluble in organic solvents and it degrades before it melts. So if you think about a plastic bottle, if you heat the plastic bottle, it is intuitive that it will melt. Whereas if you heat a piece of paper, it will start to burn. And due to this degrading before melting problem we have with cellulose, we cannot process it with normal thermoplastic processing equipment. This difficulty to process cellulose is hindering its larger adaptation in the world. So in my work, we looked at a novel solvent to make cellulose more processable. So we used a combination of choline chloride, which is an animal feed supplement, which means it's also very cheap and it's safe to use. And we combined it with an ionic liquid. Now, an ionic liquid is basically just a salt with a low melting temperature, so it's usually liquid at room temperature. And ionic liquids are established environmentally friendly cellulose solvents, and we consider them green because they are non-volatile and they are reusable. So we can literally dissolve some cellulose in a batch of ionic liquid, then we can extract the cellulose out of the ionic liquid, and then we can dissolve another batch of cellulose in the same ionic liquid over and over again. Okay, so this sounds wonderful. unfortunately, like everything, if it's too good, if it sounds too good to be true, it usually is. And ionic liquids are very expensive. So in an effort to make it more economical, we are combining it with the choline chloride without hopefully sacrificing its ability to dissolve cellulose. So with my novel solvent, we prepared different products of cellulose from different cellulose sources. So you can see at the top, we spun some fibers. The fibers we actually spun using electrospinning, which uses a high voltage to make the fibers. But unfortunately, we still have some issues there with the collection because the ionic liquid is non-volatile. However, all things considered, we actually were able to spin fibers with an average diameter of about 200 nanometers, which is not too bad. We also prepared some cellulose films. So you can see one of the films in the pictures is very clear. That clear film we actually prepared using just the pure imam acetate ionic liquid. And then when we add the choline chloride, the films becomes a bit more milky. You can still see through them, but they're not as transparent. And that is due to some small pieces of the fibers that did not completely dissolve. Okay, now you might think, oh, but this is bad. But actually, we found that small pieces of fibers that is embedded in the film actually stabilizes our film and keeps it from shrinking and warping and being all kinds of funny shapes. So this is actually a benefit to the films. And then finally, we actually extruded cellulose. Now here, we didn't use the solvent to dissolve cellulose. We used the solvent as a plasticizer. And we used a conventional extruder to extrude our cellulose on. So nothing funny, no modifications needed. Throw in the cellulose with the solvent at the one end and get your strand out at the other. And it's actually about the extrudates that I want to spend just a little bit more time with you today. So here you can see the cellulose from its beginning until the end product during the extrusion process. So we start with a powdered cellulose that we mix with our solvent, and then we compound it and we mold it, and then we end with that brownish, almost transparent test bar. And you can see the UP logo shining just a bit through the test bar, so we know it's a homogeneous bar. But this test bar contains a lot of our solvent, and we want to reuse it, so we have to recover it. And in order to do that, we wash it with water, and then we end up finally with that whitish, final, solid piece of cellulose, molded into the shape of our mold. At the moment, cellulose itself is a bit expensive, so we looked at higher value applications for our cellulose products. So we carbonized our cellulose bars to actually prepare a porous carbon scaffold. So in the last bubble, you can actually see an electron microscope image of the pores in the carbon scaffold. So you can see all the little holes, and now all those nice little holes can be used as a carrier for something. So for example, I mentioned biomedical applications. Just like cellulose, carbon is actually also biocompatible, so we can impregnate it with human cells, like bone cells, and then if you break your bone, we can place it in the break to help it heal. Another big application of porous carbon is in water treatment for absorption and adsorption reasons, and I'm sure all of my colleagues that is speaking after me will tell you a lot more about water treatment using adsorption. Yeah, I think you can go. Thank you. So the big question is now, could we actually tip this proverbial scale? Could we tip the scale in favor of cellulose, getting away from the solvent limitations and its difficulties to process, so that we can actually utilize cellulose and its wonderful properties? And the short answer is yes. So my work showed that this novel solvent is very effective as a cellulose solvent still, and we can use it to prepare different forms of cellulose to prepare different final end products. And the longer answer is a bit more, this is only a stepping stone. So with my work, I only actually opened up some new avenues for further research. I looked at only one ionic liquid and one combination of choline chloride with that one ionic liquid. So we can now investigate different solvent combinations, different ionic liquid combinations. We can look at different processing techniques, and the ones we used, we can also optimize more for different products that we want to prepare. But overall, we showed that we can, and we actually did, improve the economics of cellulose as a raw material by making it processable with a more affordable cellulose solvent. And this is then actually what I consider my contribution to science and society and industry at large, the opening up of new avenues for cellulose as a biopolymer. So scientists now have a new starting point for some further work, optimization and investigation of different solvents with the same basic idea. Hopefully this will make cellulose more usable in a larger market for higher value and high volume products, which would give the cellulose, the paper and pulp industry with all their plantations an alternative market. And for us as people, society, this is hopefully a step to a less polluted environment. If we can make products from a renewable source that are still biodegradable and is not environmentally harmful while they're being processed, I think we will create a less polluted future for ourselves. And that's why in my work, we focused on pure cellulose and keeping it pure cellulose, not changing the molecular structure, not creating a new thing from cellulose, but to keep it as close as possible to native cellulose so that when it ends up inevitably in a landfill, it can still disappear. Thank you. That's all from me. If you have any questions, you're welcome to post them in the chat. Oh, I see Sam brought a live dinosaur, a modern dinosaur.
I have one of these things. I have a few of these things in my garden. I have 2 boys, so I can attest to the scourge of plastic toys living forever.
Yes.
Thank you so much, Hester. I don't see any questions and answers just yet. Here we go. There's a question here from Washington. Thank you, Hester, for your excellent presentation. I just wanted to find out from you, do you think ionic liquids will have any effect on the biodegradability of cellulose? Do you want to answer that?
Just answer this one without typing, just by speaking.
Go for it.
So because with ionic liquids, okay, so you can change the molecular structure, so you can do some esterification reactions on cellulose with ionic liquids, but using it as we use it and as most people use it just as a solvent, you're not actually fundamentally changing anything about the cellulose, and you're washing all of the ionic liquid away. So if I can be a bit more technical, because I know Washington is also technical, we actually just changed the cellulose structure from cellulose 1, which is the native cellulose, to cellulose 2 and amorphous cellulose, and it's mainly amorphous cellulose, so it might actually break down a bit easier after it's been dissolved. And we're hopefully not dumping any ionic liquid just into the streams and water supplies, because it's water soluble. You have to be considerate of that, but most ionic liquids are actually not harmful for the environment in themselves. Yeah, there's some biodegradability studies. I haven't looked at it in my work specifically, but there is a lot. If you search for it, you will find a lot of biodegradability studies of cellulose dissolved and regenerated from their ionic liquids.
Thank you, Hester. I trust that answers your question, Washington. Thank you very much. Keep them coming in. So let's move on to our next speaker. Our next speaker is Norma Malenza. She is from the Vaal University of Technology, and her project is the preparation of a novel controlled release fertilizer coated with cellulose, starch, and diatomite. I hope I said that right. So Norma,
Yes.
Over to you, and the floor is yours.
Thank you, Samantha. Good morning, ladies and gentlemen. I am Norma Malenza, a master's student, chemical engineering master's student from the Vaal University of Technology under the supervision of Prof. Hilary Ruto. So today I will present to you a bit of my research on the preparation of a novel controlled release fertilizer coated with starch, cellulose, and diatomite. So did you know that without fertilizers, the world will need manure from up to 7 billion more cattle in order to maintain the fertility of the soil? Yes, although extremely necessary, that would be quite a smelly scenario. And also without fertilizers, only half of the world population would be able to get food. And that would only be a huge setback on our current hopes on food security. So as you can see, fertilizers are really important. But what are fertilizers? Any material that is used to supply nutrients to plant tissue or to the soil is regarded as fertilizers. And nutrients are important for plant growth, for flourishing, and for healing of the plants after the crop of fruits. And the most in demand nutrient is nitrogen. And because it is very efficient, and because it is used or is required by plants in larger quantities, it is called a macronutrient. And nitrogen is responsible for features such as the green, healthy pigment in the leaves. And as you can see on the picture on top there, we have some leaves. The left-hand side one is greener than the right-hand side one. And this is because the left-hand side one has enough quantities of nitrogen, while the other one is nitrogen deficient. The same can happen with fruits. For example, we have corn. The left-hand side one received enough nitrogen, while the right-hand side one is nitrogen deficient. The thing is, if nitrogen is not well managed, not efficiently managed, the use of nitrogen fertilizers may contribute for pollution and climate change. But in order for us to understand what do I mean or how this may happen, we'll have to take a look at the nitrogen cycle, which is in the next slide. So this is the nitrogen cycle, and our atmosphere is made up of 78% nitrogen, 21% oxygen, and 1% are other gases. But the nitrogen that we have in our atmosphere is not suitable for plant use. So in order for plants to get the chance to uptake the nitrogen, a fixation process must occur. Fixation occurs when atmospheric nitrogen is processed by bacteria that are present in soil and transforms the atmospheric nitrogen into ammonium, into nitrite and nitrate. And these forms of nitrogen can easily used up by plants. Another way in which we can have nitrogen into the soil is when anaerobic bacteria, in the absence of oxygen, produce nitrogen. Also, when dead plant material falls into the soil and it is decomposed by dead plant, by worms and bacteria, and nitrogen enters the soil. But okay, I've just explained to you how does nitrogen enters the soil. So how does the nitrogen exit the soil? Sorry, Samantha, can you go back? Thank you. Nitrogen exits the soil during harvesting, during denitrification, which is related to those nitrogen-produced bacteria. Also, when ammonium volatilizes, meaning that the nitrogen gases that get out of the soil are lighter than air and they flow up into the atmosphere. And also when we have a stream of water, either from rain or from irrigation, that washes off the nitrogen away from the plants. So some of the nitrogen exits the soil as nitrous oxide, and that gas is way much hazardous than the carbon dioxide, and it can really contribute for climate change. So an attempt to solve this issue is with the use of controlled release fertilizers. Controlled release fertilizers are fertilizers that release nutrients in a gradual, steady, and slow manner. And the release is usually triggered by factors like moisture, like surrounding pH, temperature, and more. The controlled release fertilizers, or CRFs, are usually coated, and most of the coating that is currently being used is made up from plastic that is derived from petroleum material. Oh, it is derived from petroleum. And in this project, I am going to use, or I've been using, cellulose, which is a natural resource, as a coating for the granules of fertilizer. And in this way, I aim to replace petroleum-based polymeric materials. So combining cellulose with biodegradable materials such as diatomite and starch, and let me say that starch is a fully biodegradable material that works very well as a moisture barrier, and diatomite, the mined rock with very good porosity and permeability. We can achieve a fertilizer that can effectively control the release of nutrients and is also environmentally friendly and good for our climate. So it is also important to mention that these fertilizers will be or have been designed to save water too, because they retain some moisture or water in their structure. And also, diatomite is a readily available material. In fact, South African diatomite accounts for 10% of the world's mined diatomite. So they are good materials, sustainable, and good for the use for this purpose. Okay, so this is our coating process. On your left, we have fertilizer granules. For this project, I've used NPK, which is nitrogen, phosphorus, and potassium, and urea. And I've fed them into a granulator, a pen granulator, which was rotating at a specific speed for a specific amount of time. And those variables changed because I needed to study the different factors and how did they affect the process. And then as the granules enter the granulator, as you can see there, we have spray nozzles that were used to spray distilled water and epichlorohydrin, which is a binding agent that helped the surface of the granules to adhere to the powder coating material that was deposited into it to create the layers of coating. And okay, after this step, we send the fertilizers into the drying in order to remove the remaining moisture, and then they were classified. This classification was made concerning the size of the granules and the apparent layer thickness. So by the end, we got fertilizers with a core and layers of coating that guarantee the controlled release of the fertilizer. So on your right hand side, you can see the picture of the granules at the top. And if we cut it in half, at the bottom, you can see that you have a core inside and then different layers of coating material. So in terms of advantages, for the farmers and the agricultural industry, I can say that it's very easy to use and it requires very few applications compared to fast release fertilizers. And it is easily upscaled. This process can be easily upscaled to the industrial scale production. And also in terms of benefits to the society and the environment, this CRF, for controlled release fertilizer, guarantees reduced leaching and volatilization of ammonia, minimal environmental impact, contributes to food security and to climate change mitigation. So we have reached the end of this presentation, and I thank you all for your attention.
Thank you very much, Norma. Now I know what's wrong with my garden. It needs a bit more nitrogen. So thank you so much for that wonderful and insightful presentation. We don't have any questions in the chat, but I'm sure there will be some people who may put those into the Q&A during the next presentation. Our next speaker is Nasreen Gadi, And Nasreen is from UNISA. She has been working on hydrochar production from paper sludge. That's the stuff that we get from our paper making process, but she'll tell you a little bit more about that, through hydrothermal carbonization. Some, again, big words, but let's hear it from Nasreen.
Good morning, everyone. My name is Nasreen, and today I will be presenting to you on my research work, which deals with the upgrading of paper sludge, a waste product of the paper manufacturing process, into a hydrochar using hydrothermal carbonization. Next slide. So the paper and pulp industry is a key economic role player contributing to the South African GDP. Some major producers you might be aware of are Kimberly-Clark, Sappi, PAMSA, Mondi, to name a few. The paper industry uses fibers obtained from plants or recycled products to produce paper products. Some paper products that you are familiar with are your newspapers, tissue papers, and cardboard packaging. Let's have a look at the paper manufacturing process. So, our raw material in the paper manufacturing process can be obtained from trees or from recycled products. These materials need to be prepared before we can produce a pulp. The trees have to be debarked and chopped into smaller pieces, whereas if we are using recycled products, they need to be sorted, cleaned, and de-inked. To produce the pulp, there are two methods that can be used, which is mechanical, which the material is shredded, or thermochemically, where chemicals are added to it to separate the fibers from these products. These fibers are used to produce your paper. This process also reduces waste sludge, which contains the fibers that were short and not useful for the paper making, as well as any inorganic compounds that were present after the cleaning. Water is added to produce a slurry. This pulp slurry is then sent to a paper making machine where it forms a paper web, which is pressed and dried through heating to form our final product. Next slide, please. So there are some sustainability issues which are facing the paper and pulp industry. We live in an era where we are increasingly moving towards digitalization and e-commerce. This decreases the demand on printing and writing paper. There are also increased operating costs, such as increases in labor, transportation, energy, as well as licensing and taxes. And most importantly, it's through the waste disposal management. Like I mentioned, the pulp process produces large quantities of waste sludge. This sludge has a high moisture content, and it is primarily disposed of through landfilling. However, due to the high moisture content, which is over 50%, the paper industry has to comply with government regulation where they can only landfill paper sludge of less than 14% moisture. To bring that moisture content down, it requires high energy intensive processes. So the sludge is primarily disposed of in landfilling, and landfill sites also have key environmental issues. They release hazardous chemicals into the ground, which contaminates groundwater supplies. It produces greenhouse gases, such as methane, due to the decaying of organic material. And the landfill sites also use up land, which we could have otherwise used for recreational or economic purposes. Next slide. So, our paper sludge. Is it a waste product, or do we have alternative uses for it? So some of the uses that are currently applied are incineration. However, because of that high moisture content in the sludge, it is difficult to burn it. You would first need to dry it. It could be used by the brick and cement industry to produce bricks instead of using soil, or it can be used as a soil amendment to improve the soil qualities. However, these processes also have high economic and high equipment costs and high preparation costs. So the paper sludge, it contains large amounts of plant material, which is continuously generated in the pulp production process. So this provides an opportunity for paper sludge to be used as a biological resource in biorefinery concepts and contribute to the bioeconomy. So what is all this biorefinery and bioeconomy? Next slide, Samantha. Okay. So the bioeconomy involves using biological resources obtained from agricultural products or residues, as well as municipal waste and industrial waste, to produce high value added products such as fuel for energy or chemicals. There are two biorefinery processes, the first being the biochemical conversion, which uses microorganisms to decay organic material, and the second is the thermochemical conversion method, which uses heat to cause a change in the chemical composition of the biomass. There are three thermochemical conversion methods. These are pyrolysis, gasification, and combustion. The hydrothermal carbonization technique falls under a pyrolysis technique, where it uses heat to decay organic material in the presence of water and in the absence of oxygen. The hydrothermal carbonization technique has advantages over the normal pyrolysis process. So normally pyrolysis requires low moisture content and it operates in a higher temperature range. But the HTC process has the following advantages. It has mild process conditions. So these temperature ranges from 180 to 250 degrees. It is suitable for feedstocks that have moisture content of over 50%. And there is no need for drying or heating or drying during or before or during the process. So this saves energy. Interestingly, the hydrothermal carbonization technique actually mimics our coal formation process. Coal formation, as we know, takes millions of years, where organic material decays subjected to heat and pressure. So the HTC process produces three products, namely a solid char, a bio oil, and some gases. This solid char, or as we call it, a hydrochar, can be used for electricity generation as a carbon electrode or as an adsorbent for wastewater treatment. So we know that there has been previous success using agricultural feedstocks and municipal waste to convert them into hydrochars using the hydrothermal carbonization technique, but not much has been done on paper sludge. So in this research, we will determine which conditions produce the most char, so which is optimal for char production. We look at temperature, time, and solid to liquid ratio. Also, we would like to see if the HTC process improves the physical and chemical properties of the sludge by converting it into a hydrochar. And once we determine these properties and conditions, it will assist us to develop a process to recover liquid and solid products from these paper mill waste streams. My colleague Peter will discuss how the hydrochar can be applied as a wastewater treatment adsorbent. So for my experimental setup, I'll be conducting my reactions in a reactor where I will put my sludge into it and let the reaction occur for the time that is required. Some of my products obtained are a solid and a liquid oil. The solid chars compositions vary depending on the temperatures. The top picture shows what happens at 180 degrees. So it still looks more like a sludge. And at a higher temperature, it looks more like a coal, a very fine coal. So this research will contribute to sustainability of the paper and pulp industry in the following ways. By finding an alternative use for paper sludge, we will decrease the cost involved in disposal of the waste. This will directly result in an increase in profitability. So by finding an alternative use for the biomass, we will reduce the impact of landfilling sludge on the environment. Also, one of the applications of the hydrochar is its alternative use as a fuel source, which can also reduce the environmental impact of having to use coal. And by this process releases high value materials, like we're going to determine whether it can be used for adsorbent. And if it has these high values, it will contribute to the economic development by generating revenue through sales. Thank you.
Thank you, Nasreen. That was great, very informative and well done on your research. Let's, I see there were a few Q&A questions in the question and answer box. So question here, I see Norma is going to type an answer in the Q&A, so I'll leave that to her. Let's move on to Peter Nyambe, who is going to tackle the, let me just get that up, the application of hydrochar, as Nasreen mentioned, from paper sludge as a potential adsorbent for wastewater treatment. The floor is yours.
Good morning, everyone. My name is Peter Nyambe. I'm a master's student from the University of South Africa under the supervision of Prof. Patel, Dr. Lesife, and Dr. Abdul Salam. So my project is about the application of hydrochar from pulp and paper sludge as a adsorbent for heavy metal removal. So this project is the continuation of my colleague Nasreen's project. So heavy metal are found in several industrial processes, which include electroplating, battery manufacturing, and mining activities. These elements are toxic to human and other living organisms, as they can cause diseases such as cancer and other chronic conditions, where the most toxic form being mercury, cadmium, lead, and arsenic. For this reason, sustainable and effective treatment processes are needed to treat this wastewater before it is released to the environment to prevent environmental degradation. So as you can see, as my colleague Nasreen have said, that landfilling for pulp and paper sludge is not sustainable because of the negative environmental effect. So it can be processed to solid material called hydrochar, which is processed through the process hydrothermal decarbonization process. So chemical analysis of hydrochar show that it have high oxygen content and high carbon content. The carbon content can be high, even up to 50%, depending on the source of the sludge, and it have low ash content. So these characteristics make it possible to use it as an adsorbent for heavy metal removal in industrial wastewater. So unlike char that have been processed from pyrolysis, which is biochar, hydrochar have lower surface area, but it still have high heavy metal removal because of the high oxygen content. If it have high oxygen content, it results in high concentration of hydrogen containing functional group, which are usually responsible for heavy metal removal during the adsorption process. So the low surface area can also be increased by the modification process, where we can use the physical activation process, which include the steam activation and the microwave and ultrasound treatment. We can also use what we call anaerobic digestion process, where you expose the hydrochar to microorganisms in the absence of oxygen. So, and we can also increase the oxygen containing functionally group by chemical activation. We can use the acid modification process or the alkaline modification process, which I use for this study, where I use potassium hydroxide to modify the hydrogen to increase its effectiveness for the heavy metal removal. So I've chosen the alkaline modification process because you can go back. You can operate it at lower temperature, unlike the physical activation, like a steam activation, where it requires high temperature. When the temperature is higher, it needs a lot of energy. So what motivated me to undertake this study? Water from the river system close to South Africa industrial areas have high concentration of heavy metal, which is higher than the limits set by government regulation. And this leads to a shortage of drinking water in a country like South Africa, where water is already a scarce resource. So there are several processes that are utilized to treat heavy metal in industrial wastewater, which include the reverse osmosis, the ion exchange, and the chemical precipitation process. But this process have high operating costs. For example, the ion exchange and the reverse osmosis require a lot of energy, and the chemical precipitation results in the production of toxic sludge, which will require further processing before disposal. And the precipitation process is not effective in wastewater which have low concentration of heavy metal. It is only effective in wastewater which have high concentration of heavy metal. For this reason, the wastewater from this process is not suitable to be released to the environment. So, but there's a process called adsorption, where we can use solid material, even waste material, to remove heavy metal. And adsorption process is even effective in wastewater which have low concentration of heavy metal, even in microgram scale. So there are some waste material that have been used before to prepare hydrochar and effective in removing heavy metal in wastewater, which include the crepe pomace, food waste, sewage sludge, and sawdust. So I believe that even this hydrochar that has been prepared from the pulp sludge will be effective in heavy metal removal. So the adsorption process is the addition of ion into the solid material, unlike adsorption, where the pollutants have to dissolve in a liquid or solid. So at figure 5 show the adsorption process, where we have our wastewater which have heavy metal. In this diagram, I've indicated it with the small red circle, which show the heavy metal. So when you combine it with the hydrochar, it will attach in the surface of the hydrochar. So the surface of the hydrochar have high concentration of oxygen containing fractional group, which are negative charge, and heavy metal are positive charge. That's why it attached the positive and the negative. Then we have our clean water. So the main aim of this study is to investigate the effectiveness of the hydrochar produced from the pulp and paper sludge to remove heavy metal. So at the end of the study, I want to achieve the following objectives, which is to determine the optimum condition of the adsorption process, which include the temperature, the pH, and the hydrochar dosage. So this condition affect the adsorption process. For example, the pH of the solution determine the charge on the surface of the hydrochar. So I will also investigate the effect of chemically modifying the surface of the hydrochar to see if it is effective, how much will it increase the effectiveness and the efficiency of the adsorption process. I'll also determine the physical and chemical properties of the modified and the non-modified hydrochar, which those properties include the surface area, the pore volume, the chemical composition of the hydrochar, and the functional group present on the hydrochar. So those optimum conditions, I will assess it using the synthetic wastewater. Then I will use those optimum conditions in the real industrial wastewater. I will also assess the rate of metal removal. This one, I will investigate it using the kinetics practically and the maximum absorption capacity practical. Okay. So how will this study benefit the science, the industry, and the society? So the study will add knowledge to waste and renewable resource utilization research, which will benefit the science industry. And possible and easy available adsorbents can be discovered through this research, which will benefit the industry when we can find environmentally friendly heavy metal removal treatment process, because we are using the waste material and it's easy to obtain it. It also reduces the environmental degradations. It's now the sludge, which is supposed to go to landfill, we use to make new products. And it will also, there will be also more clean water available, which will benefit the society. Can go to the next slide. So the figure show how this will the study contribute to a circular economy and the sustainability of the industry. So those blocks which have a blue wall is my current research, where I have my pulp and paper sludge. It is processed through the hydrothermal carbonization process to hydrochar, which should be used as an adsorbent for wastewater treatment. So we're going to produce clean water which can be recycled back to the plant or be released to the environment. So, but we can also produce sludge from the wastewater treatment plant, which you can also process it again to hydrochar. We can also produce what we call the spent adsorbents, which is the hydrochar, which is now loaded with heavy metal. Maybe now it's not, we can't reuse it again because it's not effective anymore. So with that hydrochar, we can form new products or we can regenerate it. So we don't want to dispose it. That's why the disposal one, I put the red cap, because if we dispose it again, it's like we're going back to what we avoided in the first place. And this sludge is even more toxic now because it has heavy metal. So I think the best thing to do is to form new products. Those products include some fertilizers, catalysts, and biocoal, which we can use in process boilers to replace the fossil coal. Or the regeneration one, it depends on the regeneration process used, because you have to use different chemicals, acids and base, and you have first to investigate if it is possible to regenerate it, or is it economically feasible, or is it environmentally friendly, you know? So to be able to understand that, I think we need further research. So, and even to generate zero waste, we need further research to know the possible product that can be produced, so we can generate zero waste and promote a circular economy. So my presentation ends here. Thank you.
Thank you, Peter. Yeah, I'll let you know if there are any questions. There's nothing in the Q&A as yet, but we'll give people a few more minutes to perhaps think of some questions for you. Well, next up is Lovejoy from the Tshwane University of Technology, and his project is on the application of cellulose derivatives in wastewater treatment. So we're sticking with the theme of wastewater treatment, and I am going to give the floor to Lovejoy.
Thank you, Samantha. Do you hear me?
Yes, we can hear you. Thank you, Lovejoy.
Thank you so much. Thank you for the opportunity. Good morning, everyone. I'm Lovejoy Dewa, a TET master's student under the supervision of Dr. Washington Mnike, co-supervised by Dr. Shepard Chitaponda of University of Pretoria. My research topic is on application of cellulose derivatives in wastewater treatment. Already, Peter, the former speaker, has covered some of the aspects that are in my presentation, so I'll just have to highlight a few things about my presentation. So, chromium is a heavy metal that is used in various industries, such as electroplating, leather tanning. Chromium in electroplating industry is used because of its shiny metallic character, which makes an object attractive after electroplating. An example is that of a motorbike with that shiny surface. Or even your kitchen utensils, they are shiny because of the electroplated chromium. But at what cost to the environment? That's the question. So, because of its extensive use and improper disposal of waste generated by these industries, such as electroplating, leather tanning, mining, contamination of surface water and groundwater is unfortunately unavoidable. In aquatic environment, chromium as a heavy metal predominantly exists in two oxidation states: trivalent chromium, which is chromium 3, and hexavalent chromium, which is chromium 6. Chromium 3 naturally occurs in the environment and is an essential micronutrient for human beings. Besides, chromium 3 is 100 times less toxic than chromium 6. As such, the World Health Organization, WHO, considers chromium 6 to be a priority pollutant of major environmental concern because of its high toxicity to living organisms. The toxicity of chromium 6 leads to health risks associated with the consumption of chromium 6 contaminated water, as chromium 6 compounds are strong oxidants that can act as carcinogens and mutagens in the body. Basically, they could result in human cancer, or they could alter the DNA structure in a body cell. Now, the occurrence of chromium 6 in surface and groundwater limits the use of affected water as drinking water. Therefore, the maximum permissible chromium concentration in drinking water, according to WHO, should be 0.05 milligrams per liter. There are conventional treatment methods that are used to treat chromium contaminated or chromium polluted wastewater, such as chemical reduction, chemical precipitation, electrochemical methods, or ion exchange. However, as Peter has alluded to, these conventional treatment processes are ineffective in reducing chromium concentration at low concentration. It is therefore vital that effective and cost-effective and environmental treatment methods are adopted for the removal of chromium 6 from wastewater. Next slide, please. Now, the previous slide The previous slide. Okay. Now, one of the methods Erodipira is alluded to is absorption. It's a very versatile method that is able to actually remove chromium-6 from wastewater at low concentrations. Why? Because absorption can effectively remove chromium-6 at low cost as compared to other conventional methods. Natural biometric materials have garnered greater attention in wastewater due to their low cost, biodegradability, and biocompatibility. In particular, cellulose, a biodegradable material, which is non-toxic, renewable, is a natural polymer that is produced by plants through photosynthesis and can be obtained from various agricultural waste products or residues such as sugarcane bagasse, rice straw, maize stalk. So on the right side of the picture, we have the structure of cellulose. Cellulose molecules. That structure is made up of several hydroxyl functional groups. Those groups are responsible for the absorption properties of cellulose. However, pure cellulose as a material has inferior absorption capacity towards heavy metal pollutants. It is therefore necessary to modify and functionalize material so as to improve its absorption capacity and its selectivity. Next page. All right, thank you. So now, what is our purpose of the research? Our purpose is to develop a low-cost, efficient absorbent material for the treatment of wastewater based on cellulose and its derivatives. So the first objective of our experiment is to compare the effectiveness of pure cellulose, which is microcrystalline cellulose, and nanofiber in the form of nanocellulose. So now these two are the cellulose derivatives that we have used in our experiments to remove chromium-6 from wastewater. Then the second objective will be to produce cellulose-based composite materials through modification of the MCC and the nanocellulose for the removal of chromium-6 from wastewater. So those two are the objectives of our project, just to compare how effective they are in terms of removing chromium-6 from wastewater. Next page. Next slide, Samantha. Now, this slide illustrates the experimental plan of our experiment. Now, both the unmodified MCC and the nanofiber and the modified MCC and the nanofiber will be used as absorbent materials for the removal of chromium-6 from synthetic water. So batch absorption experiments will be carried out as a function of pH, agitation time, absorbent dosage, temperature, with the hope of evaluating the absorption capacity and the absorption rate of the absorbent material, as well as to identify the rate controlling mechanism that will be responsible for removing chromium-6 by the absorbent material from the wastewater. Next slide, Samantha. Now this slide illustrates how we're going to modify our cellulose-based composite material using unmodified MCC and unmodified nanofiber in the presence of aniline monomer to synthesize a low-cost absorbent material, which is polyaniline straw cellulose composite. So already we've done several work on this, and then we've produced this green solid powder material as the polyaniline composite material. So now, in the process of chemical polymerization, we've identified that we're going to use an oxidant and a topant. So the name of the oxidant is ammonium peroxide disulfide, and then our topant is hydrochloric acid. Then next slide. And then, now once we've synthesized the cellulose-based composite materials, how will this contribute to science and society and the industry? So through modification of cellulose and the nanocellulose, we can develop low-cost absorbent materials with high removal efficiency, with high selectivity for different pollutants from wastewater. Then how will this contribute to the industry? It is possible that the industry could use agricultural waste products to synthesize cellulose-based materials for the removal of waste, for the removal of toxic pollutants from wastewater that they release into the environment. So it's possible for like paper industry, sugarcane industry to actually use their waste residues as cellulose-based absorbent materials to remove toxic pollutants that they produce in the production of paper and other various products. And then, as well as these cellulose-based absorbent materials can supplement the existing conventional treatment methods, such as chemical reduction and precipitation, to remove the chromium toxic pollutant at low concentrations, to establish regulation, to establish environmental standards. How will this benefit the society as a whole? There are areas that are heavily polluted with heavy metals. And then if these cellulose-based absorbent materials can be used to remove or absorb toxic pollutants from waste water before that discharged into nearby waters, that will improve the quality of the drinking water, and that will reduce the scourge of water shortage in most localities that are affected by the scourge of heavy metal pollution. And then how will this sustain the industry? The next page, Samantha, thank you. Next page. And then the sustainability. How will the industry benefit from this? Now, cellulose material is synthesized by plants through photosynthesis. So cellulose can be replenished through the photosynthesis reaction. So these plants will always be available and they're renewable. That's the benefit to the industry. And then cellulose is readily available and inexpensive. So these cellulose-based materials can be derived from, as I've said, from plants, as well as agro-based residues to be used by these small and medium industrial enterprises to remove toxic pollutants from wastewater, or could be used in water purification by local municipalities to remove other toxic pollutants in wastewater. And then the bonus with using cellulose is that synthetic polymers can be incorporated into the cellulose backbone structure to develop cost-effective absorbent materials that can be used to remove not only toxic heavy metal pollutants, but also to recover precious metals such as gold. So through these cellulose-based composite materials, there's a lot that can be done, not only in the removal of heavy metal pollutants from wastewater, but they can be used as well as in other industries to recover or even to produce packaging material and many different cellulose-based products. Thank you, Samantha, for that.
Thank you, Lovejoy. Thank you for that. Also, again, it's exciting work for our very precious water. Thank you. And we have our final speaker, and that is he is Musamba Banza. And Musamba is also from the Vaal University of Technology. Musamba's work is also around water and the removal of heavy metal ions through the production of an absorptive filter aids for the selective removal of heavy metal ions using modified cellulose nanocrystals. So, Musamba, it's your turn.
Okay, morning, everybody. My name is Musamba Banza. I'm a PhD student at the University of Vaal and working on the supervision of Prof. Hilary Hoto. The topic of the research is the production of adsorptive filter aid for selection, removal of heavy metal ion using CMC as an adsorbent. Please, can I go to the next slide, please? Yes, clean water shortage is a significant issue in Africa, especially in South Africa. And my colleague Peter already explained what is the reason of water pollution. Then I'll be explaining pollutants such as lead, zinc, copper, arsenic, cadmium, chromium, nickel, and so on, are becoming a concern in wastewater if they only exceed the acceptable range fixed by which is the Water Health Organization, and they require a selective and effective removal so that the treatment of water can meet the requirement, and those pollutants can create damage to human and the other living species, as shown in figure 2. Please, can you go to the next slide? Okay, and the proposed solution is a cellulose nanocrystal, which is extracted from waste paper, which could be used as an adsorbent to remove heavy metal ion. And to modify the cellulose nanocrystal, succinic anhydride acid was used, as shown in figure 4, and gelatin was used, as shown in figure 5. Actually, gelatin can be extracted from animal body parts such as bone and skin. And for the specific modification, it will depend on the purpose of the study, or it will depend on which type of the pollutant needs to be removed. That's why I choose those two modifications to remove heavy ion metals. Please, can I go to the next slide? And the absorption process was selected as to be the easiest one. And Peter explained already what is the problem using other processes such as ion exchange, precipitation, and so on. And absorption is the best because it's very simple, it's cost effective, and it's easy to operate, and there is no absence of secondary contamination. And the most important about adsorption is the surface charge of the adsorbent, which needs to be either negative or positive. In my case, for nanocellulose, the surface charge of the nanocellulose was negative. That's why it was used to extract the heavy metal, which was positive, such as copper, lead, and so on. And if I have to remove pollutants which are negatively charged, then the modification of the cellulose nanocrystal must make sure that the surface charge is positive, so that it can attract negative pollutants such as nitrate, sulfate, and so on. Why did I choose the cellulose nanocrystal? It's biodegradable, is non-toxic, and it can be modified. It can be modified for different removal purposes. Can I go to the next slide? Yes, and in table 1, I can see some of the results that were obtained for copper, lead, and so on. And in figure 7, we can see the waste water, which contain heavy metal ion. And on figure 8, this is what the continuous removal process which was chosen so that we can have a nice approach on the experimental design, where the different parameters were changed, such as pH, flow, initial concentration. Then after the removal, we can have an idea how the wastewater looks like on figure 9, which is more clear compared to the figure 7. Can I go to the next slide? Sorry. Okay, and for contribution to the science, society, industry, and environment, first, for the sake of knowledge, peer review publication will be produced from this work. And there is the development of biodegradable adsorbent, which we will be used not for heavy metal ion only, it can be used as well for heavy oil. Okay, and it will create a market for cellulose nanocrystal, and the adsorbent is cost effective, it's reusable, and it's biodegradable. That will have an impact on the cost and operation, and it will contribute to the clean environment, and cellulose are extracted from abundant and available sources. Please, can I go to the, oh, sorry, we can go back. And on figure 9, we can see that nanocellulose can be used in different fields. It depends on the specific applications, such as in biomedical, in cosmetic, in paint, in composite, and so on. Please, can I go to the next slide? Okay, thank you. I think this is my presentation.
Merci, Musamba. Thank you so much. Ngiyabonga. So thank you to all our speakers. I see we have answered all the questions that have been in the Q&A. And so if there is anyone who has any questions to answer, you can raise your hand, I think in the panelist, and I can give you permission to talk. I have special powers. And you can ask them live. Alternatively, just pop them in the chat while Julie is giving us the closing remarks, and we'll see if we've got time to answer them. So with that, I want to hand over to Julie Borland. Julie is a very hardworking lady that runs our process research unit for PAMSA and in our research development efforts for the sector.
Thank you, Samantha. Good morning to everyone. We've listened to 6 very interesting presentations showing the versatility of cellulose, how it can help society, environment, and our sector, and the potential innovative uses that are available to us. The students have given excellent presentations, and I'd like to thank them for that, because they've demonstrated real passion and enthusiasm for their research, and we look forward to them taking all of these skills out into industry in the future. I'd like to also thank the DSI and PAMSA for the support that they provided for this program, because this has enabled 12 students to study for their postgraduate qualifications. And this is a really significant achievement. And finally, I'd like to thank all the participants for taking their time to attend these webinars and for supporting our young engineers. So thank you for that. Thanks, Samantha.
Thank you, Julie. Thank you so much to everybody who has attended. I see we've got a number of our members who have attended, some people who do some support work for PAMSA. We have just a comment here from Rosalind Santos. Congrats to the students, and wonderful to see your research. So to the students, thank you. You are making a contribution to society, to industry, to science, and yes, it's exciting, and we do hope that this research will take you far. So I want to just wish you all a really good weekend and a wonderful day. We've finished earlier than we originally anticipated, and I would ask you to stay safe. And just remember that August is nearly over and spring is coming. So there's something to look forward to as our days get longer and our days get warmer. So thank you again to all our students, to the university staff and lecturers that support these students along the way. Thank you for all your hard work behind the scenes. Thank you again. And we'll hope to have another one of these in maybe later in the year or next year. So thanks again and have a good day.